Hello. Let's see. Okay. Everything should be ready. Do you hear me? Do you see the desktops? Everything seem okay? I'm trying to pop up some windows. Does everything seem
Yes,
okay,
I
right?
can hear you.
Pardon me?
I can see and hear you.
Oh, okay,
Hear you,
great. Yeah,
Stephen.
thanks. Okay. All right. So this is the last week of the semester. What I wanted to just show you some things we could do with what functional programming is really for. I was going to show you some examples of things that we can do with our language using functional programming. But first, let me ask if there's any question about the homework assignment. Does anybody have any question about the static analyzer? Last week talked about it a little bit. Does anybody have any questions about any more questions they want to ask right now about the static analyzer?
I have one quick question.
Sure.
When I check for runtime checks, using find, I only come up with 14 and it says there's 38 places.
That was in language 7, not this version of language 7.
Okay, so go back to our last.
Yeah, the language
7.
Right. That was language 7. Here, let's show it. That would be.
I thought about that, but I just wanted to make sure.
Yeah, I meant this language 7 here, not the language 7 in the homework assignment. So like here, oops. Okay, if you go to the evaluate in here, find one of them. Okay. Yeah, see there's, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33.
Okay. I was doing 34. The one that was in the file.
Yeah, that's the whole point. See, that's the whole point. That's how many got eliminated. Then if you look at the one in the homework assignment, okay, now I think I download, see. Oh, I didn't unzip it yet. If you go to the homework assignment, and you look at this one, and you look for all the runtime checks. Now there's just, let's see, I changed, there's only one runtime check, and all the others now are runtime type checks. Okay, so I changed their names. So now what's left mostly is runtime. And see, now all the type, it's actually very important to realize that the only thing left in here are these ones that check the tags, the type checks. And that's pretty much what you find in a real modern interpreted language like Python or JavaScript. They have to check the types at runtime on everything they do. Okay. Now notice that I only have one runtime check that's not a type check left. Okay. I forget what this one was. This was checking that the number of actual parameters is equal to the number of arguments. This was checking that the number of arguments was equal to the number of parameters. So that's not a type check. That's a runtime check. Okay. That's the only runtime check left in here that's not a type check. Everything else is saying, I compute a value and I need to check that it's, in this case, really a Boolean. Here, check that it's a Boolean. Here, check that it's a Boolean. Here, check that it's an int. 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 Okay. Here, check that it's a lambda. Okay. So now, what are the runtime checks that are all gone? Are things like checking if something is a valid name, checking that something is defined. See, those are the things you're now doing in static analysis. There's a type check. There's a type check. See, formal parameter is a valid name. Tree degree is 3. See, those are all the things that you moved into the static analyzer. Okay, so pretty much the only thing left, and that if we had more time in the semester, the next thing to do in this theory is to do the type checks in the static analyzer and get them out of the interpreter. But then you have to have a language that has types. Then it can't be JavaScript or Python. Then it's got to be a language like C. Yeah. So in a language like C, we could then start putting types into the language, and then we don't even need the runtime type checks. Then the static analyzer can check that you only assign an integer value to an integer variable, and you only assign a Boolean value. You only use a Boolean value in an if statement, things like that. That can be, right now that has to be done at runtime. So like this is the homework 5.1. If you look for evaluate if, see, here's evaluate if. The first thing it does is it checks the first statement in the if. It has to check if it's a Boolean. There's no way the static analyzer can know if something is a Boolean or not until it's been evaluated. Okay. If there are types in the language, we don't have to do this step anymore in the interpreter. If there's types in the language, if every variable is identified as either an integer or Boolean, and every function identifies what its return type is, then you could statically analyze everything, and then you don't need these runtime checks either. These would become analysis time checks. I wish we had time. And the next time I teach this course, I may actually rejuggle things around to do that, to get to that last step. Now, that's not functional programming. That would be like, that means that after language 7, you could do 2 different directions. Our language 8 was adding functional programming to language 7. The other possibility was to take language 7 and add types to it. And then you could add functional programming to the types also. You could do both. You could do one or the other, or you could do both. Okay. So right now, after language 7 comes the closures, but after language 7 could come type checking. Type checking and closures combined starts getting to be a lot. Okay. But it could have been type checking after language 7. And I might still do that. Might do two language 8s, one with closures and one with type checking, and not try to combine them together, but just do 2 of them separately. Okay. But the thing is, for you to get a sense of what programming languages are like, what are the things that programming languages are trying to do? They're trying to run as quickly as possible. Okay. These runtime checks slow you down, but how do you get rid of them? You're seeing that a fair number of them can be gotten rid of with a static analyzer. And you're doing the ones that are pretty straightforward. Getting rid of the type checks, well, JavaScript doesn't get rid of them. JavaScript doesn't want to have types on variables. I'm not sure why. And Python also doesn't want types on variables. They think it makes it easier to program the language. They think it makes it easier for programmers, but it slows the language down and it makes the programs error prone. But it kind of does make it easy to teach the languages to novice programmers. And that was actually the motivation in Python. Python, part of the reason for inventing it was to make it a language that could be taught to middle school kids. Actually, the guy who invented Python really had in mind the idea of teaching the language to middle school kids. So he wanted it to have a low barrier to entry. So he decided not to have types, because types are just one more thing to teach. And then to his surprise, the language became tremendously popular, and people use it all the time. And it's still a big controversy whether it should have types or not. Okay, so because you can't, to get rid of these runtime type checks, to get rid of these, you have to have typed variables. You have to say X is an int or X is a Boolean. Okay, and functions have to say I return an int or I return a Boolean. And Python doesn't want to do that, so Python needs these. Okay. What about other questions for the static analyzer? So I probably should have renamed things. Like in here, it says language 7. Well, this is the evaluator. It is still language 7, but this is a different evaluator. Okay, so this is the exact same language 7 here and here, but it's not the same interpreter for language 7. So it's the same language, but different interpreters. In this one, there's no static analyzer, so the interpreter does all the runtime checking. In your homework assignment, you're writing the static analyzer, so the interpreter can offload a lot of its responsibility on the static analyzer. Okay, and that can speed up the interpreter quite a bit. If you wanted to, you could do benchmarks between this interpreter and this interpreter. You'll find out that both are tremendously slow, but this interpreter should be a little bit faster on certain programs than this interpreter is, because the homework 5 interpreter just doesn't do that many runtime type checks. Yeah, you do more work at analysis time, so you can do less work over and over again at runtime. Okay, like I said, programs like Python and JavaScript, modern languages, they have this as static, and they have very powerful static analyzers. Okay, but they're stuck with a fair amount of runtime checks in their interpreter because of the lack of types. Okay, so the languages have very sophisticated static analyzers. They're not baby languages. They do as much static analysis as they possibly can to try to catch as much stuff at runtime. At compile, well, at compile, what essentially is compile time, but it's and now you can call it analysis time. And Python, there is a whole world of Python where people add type informations to their programs, and then it gets static. They have what are called type annotations. You can do Python type annotations, okay, which are hints that you put in your code that are not part of the Java language. They're not part of Python language, okay? See, they're type hints. You can put them in your code in a certain way. I forget exactly what the syntax, it's kind of funny syntax, but you put these hints in your program. The hints are used by a static analyzer, but they catch errors, but they don't change the interpreter. Since the interpreter can't rely on these hints being in your program, then it doesn't change the interpreter. It just helps you catch more errors before your program runs. So if you want, you can put type hints, type annotations into your code. Python has a sophisticated static analyzer that will look at your type hints and tell you if you made a type error, but that doesn't affect the Python interpreter, because the Python interpreter can't assume that the static analyzer was used. The Python language doesn't require it. So a lot of Python programmers use these. A lot of professionally written Python code uses the type hints, but that's just to catch bugs. It doesn't help speed up the language because the interpreter is not defined to rely on these things existing. Your code doesn't have to have type hints in it. Okay, so it's just weird how there's all this chasing back and forth between types. Why don't they just make the type hints required? Well, but then the language would be a little bit harder to teach. The language would be a little bit more, the language would have types in the language. Okay, so they basically have types in the language. Now you can annotate everything, but you don't have to use it. Oh, the annotations look like this. See, that's saying I have a function that takes a parameter name, and the parameter is a string. That's that notation comes from Haskell and ML, but that's the type. You put the type after the variable name, as opposed to Java, C, and C++, where you put the type in front of the variable name. Okay, so this is a really commonly used type notation. You're used to saying things like int x, double y, and that language that's used in, that comes from C, C++. Well, C is the one of it. C++, Java, JavaScript. Well, JavaScript doesn't use it because JavaScript doesn't have types. Okay, So you do this, okay, C, C++, and Java. Then there's a whole nother world where you do this, X colon int Y colon double, okay? And this came out of the functional programming world, I think, invented this notation, but this notation is used in ML and in F# and in Haskell and a few other languages. You write the variable colon, then the type after it, okay? So if you're like a function in Java, you'd write int f of int x. So there's a function that takes in one parameter that's an int and returns a parameter that's an int. In this notation, it would be written f x colon int colon int. The input to the function is an int, and the function returns. So you put the types after, so this would be after the function. Yeah, you'd say the function returns an int. So that would be the equivalent of this. Okay, so Python, for its type annotations, adopted the more functional syntax. Instead of adopting the C, C++, and Java syntax, it adopted this functional syntax. Okay, and I think Rust also. Yes. See, they also adopted the more functional notation. So even though Rust is not a functional language, Rust also picked up on this notation. So guess is of type unsigned 32-bit int. Okay. Okay. So Rust uses that same notation. So Python uses it as a hint. You know, you're not required to use it. Now, see, JavaScript. Oh, another good example is Typescript. Typescript is a way of adding types to JavaScript. Okay, so Typescript also adds, and again, it's kind of like, and see, notice that they use this. So this would also be Typescript. Typescript uses the functional notation. So you have first name has type. Let's see. No, that's no, that's not type. That's a key value pair. No, I'm sorry. That's key value pair. Let's see. What was the notation that Typescript used for types? Let me think. Okay. I'm sorry. JavaScript uses colon to mean key value pairs. So let's see. Looking for an example. I'm trying. There's so many of these languages, I forget their different notations. So yeah, here. Yes, oh yeah, right there. Yeah, so they use, types. So make reading takes a parameter s, which is of type string, and the function returns a string. Okay, and then it has a local variable that has a type number. Yeah, and it also uses colon to separate keys and values in key value pairs. So it uses colon for two purposes. So TypeScript uses this type notation too. Variable colon type, variable colon type. Okay. So TypeScript and Rust, two recent languages, picked up on the notation of the older functional language. This notation goes back at least to ML, which was from the 70s. ML used this notation back in the 70s and 80s. So it's an old notation. Okay. Java picked up on the C. Well, Java did what C++ did, and C++ did what C did. And C, I think this notation existed before C. That notation may have existed in a bunch of languages in the 70s also. I think Pascal, I don't remember. Yeah, there may have been other languages that use this type before variable versus type after variable. Okay. Notice that this needs a punctuation mark There's no punctuation mark here. That's interesting. This just says type space variable name, no punctuation. There's a punctuation mark to separate the type from the name, the variable. Okay. So notice that this is kind of quirky stuff. Python has types, even though the interpreter doesn't use them. So the types in Python are just hints. TypeScript is somewhat like that. TypeScript compiles to JavaScript. JavaScript doesn't have any types, but TypeScript does have types, but it compiles to JavaScript without types. So essentially, it's JavaScript with types. So TypeScript is JavaScript with a type notation, kind of like this. But see, since this is JavaScript with a type notation, the type notation does not end up speeding up your programs because the interpreter is still JavaScript. The interpreter doesn't know that you've checked your program for types, so it does all the runtime type checking anyway, just like Python. The Python interpreter doesn't know that you did type annotations, so it's still going to check everything at runtime. So Python and TypeScript both have this weird thing that you put the types in, they get checked before your program runs, but then all that type checking is kind of almost, it catches bugs. It doesn't help speed up your code. It does catch bugs, but doesn't speed up your code. In the case of these languages, C, C++, and Java, that's why they're fast. Oh, now Rust is in between. Rust, the type checking is used by the compiler. Okay, so Rust is not like TypeScript and Python, and neither is ML and F#. They're not like Python either. They use the type system in their compiler. So for those languages, the types speed you up. So it's Python and JavaScript that are the oddballs, where you put the type information in there, but it doesn't do you any good at runtime. The type information is used to check for errors. It helps you with debugging and checking for errors, but has no benefit for speeding up your program. Why would they do that? Why would they finally end up saying, well, yeah, maybe types are a good idea, so let's have you put types in your program, but then we won't use them at runtime, so our programs are still slow. Well, the reason is because, like in the case of TypeScript, nobody can go back. It's too late to change JavaScript. It's just too late. So we just can't do anything about the fact, unless the world's willing to throw JavaScript overboard and start with a new language in the browser, which I think would be a good idea. And then they could have something that's way faster because they could just say, we're going to use types. And same with Python. Python would have to pretty much throw 30 years of Python overboard, and say, well, we're going to require types now. Though, because I don't think that many Python programmers use the types. Even though they could put types in their code as hints, I don't think that many Python programmers do. I think only people writing super serious Python code do that, which is not the vast majority of Python programmers. So I think people doing like data science in Python probably don't bother with the type information. I bet most of the data scientists don't bother with it. Okay. All right. So this is the core. These are kind of the core ideas in programming languages. Why are the types there? What do you do with them? Now you can, in our homework assignments, you should be able to get a sense of why. Let me say that. Huh. Yeah. We see what happens when you don't. The key with this homework assignment, and the key with these interpreters, is you see what happens when you don't have type information. You saw how many runtime type checks. You saw how much this evaluator had to do runtime checks in it. But we got rid of most of them with the static analyzer. But we could not get rid of the type checking. So even here, that's the next hurdle, is try to get rid of the type checks in the interpreter. They really do slow the interpreter down quite a bit. It's one of the main reasons why Python and JavaScript aren't as fast as they could be. They're just too slow. And it's because they have to do massive amounts of runtime type checking. Every if statement, you think of it, if you put an if statement in a for loop and the for loop iterates 1,000,000 times, you do the same type check over and over again on the if statement inside the for loop. You know, and there are some optimizations that try to sort that out. You know, so like what I mean is, like, if you do if you have a for int I equals 0, I less than 1 billion, I plus plus, okay? And then in here you say, like, if I equal 42, do something, okay? Now, if you think about it, that's a Boolean expression. You know, you can see that, you know, that's a Boolean expression, okay? So you would think that you don't need to keep checking a billion times whether, you know, when you look at the interpreter, so then you go to the interpreter and you look at evaluate if. Evaluate if, every time it evaluates that thing there, it does a type check, even though it's checked the exact same expression 1 billion times. Now, there's nothing that's going to make that thing sometimes give a Boolean and sometimes not give a Boolean. It's possible to write interpreters that kind of only need to check that guy one time, that are kind of somehow clever and say, well, you know, this guy's in a for loop, you know, of course, you know, the 10 millionth time you execute this is not going to be anything different. But then somebody goes like this. Where G is a Boolean valued function. Well, how do you know G is a Boolean valued function? Yeah. Suppose down here you have G of int, suppose you have G of I, yeah, and it does some calculation. And it's supposed to return a Boolean, but maybe, how do you know it always returns a Boolean? See, the interpreter, you can make this as complicated as you want. How can the interpreter guarantee absolutely all the time that G is going to return a Boolean? Well, if G was declared to be a Boolean function, you know, if G was declared to be a Boolean function, but that requires type information. If it's Python, who knows? Maybe G sometimes returns a Boolean, sometimes it doesn't return a Boolean. So you're back to having to check this guy a billion times. You know, if it looked like this, maybe you could get away with saying, I don't need to check that a billion times because the code's not changing. You know, the 10 millionth time through the loop, it's still checking if I is equal to 42. But things get even more and more complicated when you do that. You know, can you absolutely guarantee that every time you call G, it's always going to return a Boolean, especially if G in the middle of it calls some function H? You know, so then how do you know what G does? Well, you have to know what H does. You know, so you're basically having to check the type of this a billion times. You know, if there's no type information in the language, the interpreter really just cannot know when it evaluates the first part of an if statement for sure that it's going to get a Boolean value. So it has to, it evaluates the expression and then stops to check, did I get a Boolean? If you have a compiled language, the compiler would know G returns a Boolean. You know, the compiler would know exactly what these things are. And the compiler would just say at compile time, oh, you goofed up. G sometimes returns an int, so you can't do this. So that gets a compiler error. Or the compiler says G always returns a Boolean. So, and then the if statement can safely just never do that. You know, then the if statement can just assume that when it evaluates this expression, in fact, it could even be evaluate Boolean expression there, something like that. But it can't be that actually, because it could still be a function call. You know, it isn't that this is a Boolean expression. It's an expression that's guaranteed to return a Boolean value. There's a big difference there between a Boolean expression in our language The Boolean expressions look like this. But an if statement isn't supposed to be a Boolean expression there. It's supposed to be an expression that returns a Boolean value. That could be a function call. It could be an apply. So I could put a function call there, but then I want to know that that function call returns a Boolean value. That's when I start needing a type so I can start chasing this stuff down. The if statement just requires that this be something that returns a Boolean value. It cannot require it to be a Boolean expression. That would restrict the language too much. In the old days, they actually had languages where an if statement had to have a Boolean expression there. You could only write an and or not, you can only write a very limited set of things right there so that the language could guarantee that that was a Boolean. But that makes the language way too restrictive. That's going back to the 1950s. Since at least the 60s, an if statement would let you call a function right there. If the value of that function call is true, do that. If the return value of that function call is false, do that. You can do anything you want there as long as it returns a Boolean. But you either have to type check the return value or have a compiler guarantee that expression, have a compiler guarantee that expression returns a Boolean so that you don't have to type check it. The third alternative is to not have types in your language and not do the runtime type checks either. Does anybody know what happens then? You don't have types in your language, but you eliminate the runtime type checks from your language. So it's fast and it's easy to program. So you see there's a few people who've done this. What kind of language do you end up with then? It's fast, easy to program, but what price do you pay?
Error prone.
Very error prone, right? And no error message like, oh, I threw an exception because you passed me an illegal value. You just get silent errors. You get bizarre, silent, unfathomable, almost impossible to track down errors, because this thing will evaluate to something, and if you just assume it's a Boolean, but in fact it was really an int, then when you get down here, all kinds of weird things can start happening. So the language just assumes that things are returned the right kind of value, even though they might not be. And it just plows ahead, always assuming that it got the right kind of value back. Okay. And there's some languages like that out there. I can't remember. I think maybe Forth is like that. That just, it's up to you. If you write your code sloppy, you pay a price. If you write your code really, 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 really carefully, you get speed and you get code that doesn't need types. Not that that's really all that, it's a weird thing, this idea of not wanting to have types in your code. You can do some really clever things. If you don't have types in your code, if you're not forced to declare types, you can actually write some super clever code, but it becomes really difficult to read and debug. You can write code where a function takes in ints and strings and does interesting things with the ints and strings, and you can just do all kinds of bizarre things if you're not forced to declare your types. And modern programming languages decided that's just all that cleverness is just begging for problems. It's just begging for a bug to show up 5 years later where the person who wrote the code has left the company and now nobody knows what the code does, but all of a sudden a bug is surfaced and you just have no idea what the problem might be. Okay? Whereas at least with types prevent you from doing a lot of stuff. They really restrict you. So they kind of put a straitjacket around you, but for your own protection. So types restrict what your code can do, but they kind of keep you on a straight and narrow path where you don't write really crazy code. Okay. So you can strip out all the type checks if you want, but then you're just end up with when something does go wrong, when something does return the wrong type, you just get silent errors and you have no idea where they came from. You know, by silent errors, I mean the program keeps going forward, even though there's been a mistake. The program may not crash till later on, or the program may just return a completely nonsense answer and you don't know why. But the program just continues computing even though something clearly has gone wrong. You know, where a type check would have noticed that something goes wrong, you remove the type check and just let the program go forward. Okay. Some languages, some languages work that way. Okay. Python and JavaScript don't work that way. They do the runtime type checking. They will throw an error if you do something really strange. So if they detect that you're trying to add, say, a string to, well, something that would be like if you add a string to an int, they just convert the int to the string and concatenate. So if it would have to be something like adding an int to an array. What would it mean to add an int to an array? Well, you could add the int to every element in the array or something weird like that. But usually if you try to add, if you have like really messed, or if you try to add an array to a string, things where things just really cannot be made sense of, then they'll give you a runtime error. Though they're notorious for trying to do the best they can. Like if you add an int to a string, well, even in Java, if you add an int to the string, you convert the int to a string and concatenate. That may not be what you meant. It may actually, in your case, in Java, you know that you're doing that on purpose. In Python and JavaScript, it might just be an accident. You may just be adding an int to a string by accident, not realizing it. What if you multiply two strings together? Or if you multiply an int times a string. JavaScript, I think, tries to make sense out of a lot of those things. A lot of what should be runtime type errors, JavaScript actually finds a way to make sense out of them in some, and that's one of the things that makes JavaScript a controversial language. It has weird ways of making sense out of what probably should be runtime type errors. Okay, like I don't know if you multiply an int times a string, I don't know if it'll actually do anything. Well, actually, you can find out. Five times cat. Well, didn't throw an error. Notice it didn't throw an error. It returned a value. Like what? I can do var x equal 5 times cat. X is a variable. X has got a value. No runtime error there. JavaScript's nuts. That probably should have been. Let me see if I can actually generate a runtime error. Does anybody know how can I generate a real honest to goodness type error in JavaScript? You have to work hard because JavaScript really wants to try to make sense out of every stupid thing. What if I do string times string? Still not a number. See, it's just basically trying to pretend that it gives it a type, it gives it a value, it gives it the value, not a number. Anybody, let's see. Does anybody know something that'll honest to goodness give a runtime type error in JavaScript? Anybody? Let's see. String.
Try your array idea.
Yeah, that's what I was going to do. String plus a list of numbers. Oh, see, what did it do? It concatenated the string with the first number in the list. Okay, so I mean, I could do var y equals cat plus 1, 2, 3, 4. Okay. Y is that string list. Cat 1, 2, 3, 4. Yeah. Now if I multiply, I'm back to not a number. Yeah. Still doesn't want to throw an error. Okay. It still is choosing to just let it go. I mean, y is a variable in my program. My program continue running. Y is a variable. It's got a value called not a number. Okay, My program hasn't crashed yet. At some point my program might crash. Boy, let's see. What if you multiply two lists?
I think it might just do union or something.
Yeah, I bet it'll do something.
Oh, maybe not.
Still not a number. Okay, yeah. See, that's one problem. I think not a number is a catch-all value for almost anything. It might even. I don't think JavaScript makes everything not a number. I do think there are valid, legitimate runtime type errors. I thought there were, though it's starting to look like everything is not a number.
Can you assign that to a variable?
Oh,
like
yeah, sure. Let's see. What means, like I can say val z equals, well, no, if I type NaN, I don't think that.
I mean the multiplication of the
oh,
arrays.
Yeah, sure. Yeah. Oh, not val. Var. I get mixed up. Val is ML. Var is JavaScript. Okay. So what's Z? Z is not a number. See it. Z. I can assign it to Z. Yeah. I could even do things like what's Z plus 5? What's Z plus 4? Well, not a number. No, notice it's not crashing. What's Z times 0? Not a number. What's Z plus cat? Look at that. What's
Nancat.
Nancat. Yeah, it's a string. Notice that the program is continuing on with a nonsense value. It's not thrown. It's not thrown an exception yet. The programming language is not thrown an exception. It is basically just taking your ridiculous value and just continuing on with it. I don't know what you can do to get types. Let's see if we can Google TypeScript runtime type error. See if there are any. Yeah, I don't know if. Yeah, I'm not even sure how to generate one. Everything we've tried.
So is that in sloppy mode right now, or?
Yeah. I think since I just opened the interpreter and just started typing, I'm in. Yeah, I don't know. Can I type strict here? I don't know if I can type strict here. Yeah, I don't know if you can throw the console into strict mode. Yeah, I don't know if you can throw the console into strict mode. I don't use JavaScript all that much, so I'm nowhere near anything like an expert in it. So I don't even know. But yeah, the console I think by default is in non-strict mode, so it lets you do anything. Some of these things I typed would have been caught in strict mode. Okay, they wouldn't show up as they would. More things become errors if you're in strict mode. But this is raw JavaScript. I mean, this is essentially the JavaScript language itself. Yeah, I don't know. I don't know what you would have to do to get JavaScript to essentially do what our language does here. When it says the runtime, the type of that thing is wrong, so we're going to throw an exception. Python, I think, will be much more likely to do this. If I started up a Python interpreter, I don't remember if I have one on here right now, but it probably would be more likely to throw type errors. JavaScript is notorious, utterly notorious for wanting to keep on going. It came from the idea that browsers shouldn't crash. Web pages should load. So the idea was that no matter what kind of idiocy was in the JavaScript code, it should just keep on going so that the web page can be displayed. So the JavaScript language was designed to just to somehow try to make some bizarre sense out of everything. Like Z is not a number, Z plus cat is nancat. Yeah, that's really weird. And there's whole pages of the famous phrase. Yeah, you look up what TF and you'll find lots of references to JavaScript. Okay. Yeah. JavaScript has a whole, there's a whole subgenre of JavaScript things that are weird. One person's famous for having created a whole list of these things. Like here, we can, yeah. They're claiming that empty is equal to not empty. True. Yep, there it is. See, empty list is equal to non-empty list. Okay, yeah. That, how do you design a language like that? Or, or, oh, that one didn't work. So I don't know, why that one didn't work, but this one did work. Empty list is equal to not empty list is true. Okay, so the language is full of bizarre things like this. Some of these are typing things, and some of them aren't. Like this is not a typing thing. This thing here, that empty list is equal to not empty list, that's something that's not a type issue. I'm not sure, I can't remember what the logic was behind that, but it's not a type issue. I don't know if there's any of these. It's got to do with this truthiness. This one's got to do with the idea what they call truthy, which things are truthy. I wonder if they even have any examples of a runtime type error. Yeah. Okay, so JavaScript's really weird. Yeah. But from our point of view, what the point is this idea that you interpret things, and then you need a certain kind of value. If you're an if statement, obviously an if statement or a while, another one is a while, that needs to be a Boolean value. That needs to be a Boolean value. Without type information in the language, how can you guarantee that there's a function call there, that the function call returned a Boolean? Okay, so in our language and in JavaScript and Python, you can't. So you have to runtime type check. You have to say, okay, evaluate the expression, make sure I got back a Boolean. Okay. JavaScript actually makes it so that if this thing is supposed to return a Boolean, if you need a Boolean here, you just convert it to a Boolean. What JavaScript tends to do is it gets this thing back, and instead of checking it, it checks it's a Boolean, and if it isn't a Boolean, it tries to figure out a way to force it into a Boolean. That's this truthiness thing. So like a string, like in C, 1 is true and 0 is false. JavaScript has a whole bunch of rules like that. So if it gets back a string, I forget if strings are true or false. Cat equal true. So cat is not, so cat isn't true. So then cat equal false. Oh, cat's neither true nor false. See, so if it's not true and it's not false, notice it's treating it as it's treating it kind of like if it was a Boolean, if cat 0 or Oh, see, how do you write if statements in JavaScript? I thought it was. Isn't it just if cat? Isn't it the same thing as in Java? Oh. Yeah. So cat was false. Notice it treated it as a Boolean. See? If cat 0, else 1. Okay, so in here should be a Boolean expression. It was a string. From JavaScript's point of view, it tries to if it needs to be a Boolean here, it shoehorns it into a Boolean. So it decided the cat was false. Even though up here it said cat is false, here it treated it as false. Notice that the language is bizarre, okay? This should be a Boolean. Booleans are either true or false. Since I got 0, it must have treated this as false. But cat equal to false is false. So cat's not false. But it acted like false here. Yeah. Try to make sense of this. The language is really bizarre. It means that the interpreter is really strange. Yeah. The interpreter in the if statement evaluates the if part, the Boolean part. It gets back something. In our case, we check that it's a Boolean. If it's not a Boolean, we throw an exception. Their interpreter gets back something and then tries to make sense of it. So instead of just saying, if it's not a Boolean, we throw an error, it says, well, let's see, if it's a string, we do this. If it's an integer, we do that. If it's a list, we do this. If it's a strut, we do this other thing. So the interpreter has this bizarre way of trying to make sense of, so instead of doing a runtime type check, the interpreter does something weirder. It tries to shoehorn whatever was there into being a Boolean value. Okay, that's made the JavaScript language really famous for being a flaky language. Like you can't make sense out of it. Many of its decisions are totally arbitrary. Like cat's not false, but it acts like false. Okay, I don't know if any. Let's see. This is a famous example. The string true acts like false, but there are places where the string true acts like true, if I remember right. Okay, this is the string true, and it acted as false. Okay, if I drop the quotes, then it's the value true. No, I thought there was. Doesn't JavaScript have a true value? Oh, I'm sorry. Wait a minute. I'm doing this. This is the true part, right? I was talking about thing. So no, it's treating cat as true. I'm sorry. It treated cat if true, then return this, else return this. So it treated cat as true. Okay. Even though cat's not true, it treated it cat as true. Okay. And it treated the string true as true. I think I guess it treats every string. Oh, I know. Let's see. Try the empty string. The empty string is false. Yeah. The empty string is false. Non-empty strings are true. So a non-empty string is true, and an empty string is false. Okay. So yeah, it just tries to shoehorn things. But on your hand, empty string goes false is true. Non-empty string is, see, but not, see a non-empty string equal to false is true. But the non-empty string in the Boolean part acted as true. Okay. So here, non-empty string is equal to false. Non-empty string equal to false is true. So that means this thing should act like false. But up here, it acted like true. See? That acted as true, but here, non-empty string go false is true. So the language is self-contradictory. It's trying to do bizarre runtime type, whatever the right word for this is. It's trying to do type conversions. It's trying to do bizarre runtime type conversions, and it's tripping all over itself because it doesn't do the same kind of conversion all the time. So here it did one kind of runtime type conversion, and here it seems to be doing a different kind of runtime type conversion. Okay, so yeah. So what's it doing? You evaluate something, you get back a result. We say it must be a Boolean result. They say it should be a Boolean result, so let's try to force it to be a Boolean result. And then they do kind of weird rules to try to force the return value to be a Boolean. But in one place in their code, like in this here, in the if statement, they might force it to be a Boolean value one way. Somewhere else, they force it to be a Boolean value a different way. Does this make sense? See, I mean, you know, that acted as true. Wait a minute, okay. But see, 0 equals false is true and 0 equals false. Yeah, 0 equals false is true, 0 equals true is false. So that certainly seems to say that this guy is false, but he acted as true here. Okay, and the empty string equal to true the empty string equal to true is false, and the empty string equal to false is true. Okay. Oh, another thing is JavaScript has a triple equal sign. See the difference? Empty string triple equal false is false. Empty string double equal false is true. So there's these two different, there's double and triple equal signs. That's another thing that makes this stuff crazy. Okay. The difference between the double and the triple equal sign. I forget which one you're supposed to use where, but they don't give you the same answer. So empty string is false under double equal sign, and empty string equals false is false under triple equal sign. And for non-empty string, so you get different answers. Should a language be designed this way? I don't think it should be. And a lot of people don't think it should be. But there's a lot of people who seem to like JavaScript. They think it's somehow good. They think it's a good idea. Like I said earlier, a lot of this was meant to make the browser keep going and not give users error messages. Okay. But at the same time, it just creates a false sense of going on. Yes, the browser goes on, but just something's going to happen. Something's going to go wrong eventually anyway. If you're returning bizarre types and you're not doing things the right way, you're just postponing the inevitable if you don't give an immediate error message. And waiting to give the error message till something just really catastrophically goes wrong is not a good idea. So the motivation was to try to keep the browser moving, but you're just postponing the inevitable problem. Okay. Notice that these uncaught are syntax errors. I have not been able to get a runtime. See, I'm getting, the errors I'm getting are mostly syntax errors. Here I got something. Oh, I typed the word strict. I don't know. Strict just doesn't mean anything here. I have not been able to get a runtime type error. Nothing I've done yet has been able to give me a runtime type error. I don't even know. Maybe you can't. Maybe no matter what you do, JavaScript is going to. It might even be the case. I don't know. I thought there were runtime type errors in JavaScript, but I might be wrong. It might be the case that they've managed to make everything make sense at runtime, so that nothing can go wrong. No matter what return value you get, you can somehow make sense of it. No matter how bizarre you have to stretch logic, you can make sense of any return value. Okay. Anybody think of anything that might, does anybody know something that could actually generate a runtime type error in JavaScript? We've done some pretty weird things here, and they always came out. That's an object. That's the object notation. So when you put there's an object with field X and value 3. What if I add an object to a string? It stringified the object and just concatenated it to the string cat. So it just stringified the object. Well, if I multiply an object with a string, back to not a number. Make you think that maybe NaN is just like a catch-all. If you can't make sense out of something, just make it NaN. But that's not an error. You know, it's not stopping the program. It's, you know, I can assign that to a variable. Okay, I have a variable Bob. Notice I don't have a variable Alice. See, but I could let Alice see. Now I have a variable Alice. See, I have a legit. See, that's different than before. Alice was an undeclared variable, so that was a runtime error of an undeclared variable. Now I have Alice is declared, and it's got this nonsense value. But notice it didn't, you know, it didn't stop the program to give Alice a ridiculous value. I gave Alice a ridiculous value, and Python just said, okay, we'll interpret this as not a number, and so it's just not a number, and your program just goes on. Okay, you've declared a variable Alice. You can pass Alice to a function, you know, and you know the function will just see Alice as holding the value NaN. But that may not, you know, eventually at some point, Alice being NaN may cause something to blow up. But, you know, how would I know that the problem came from way back over here when I defined Alice? Okay. Yeah, I mean, you know, you can just keep playing around with this stuff, like, you know, add strings to, you know, I think almost anything you do, add strings to objects, multiply strings with objects, subtract them, do it, just anything you do. It's very possible that they're all going to be not a number. Okay, programming languages are interesting things. I mean, understanding the issues is what I really hope is important here is learn JavaScript, but also understand the issues. What did the JavaScript people decide to do as opposed to what could you do? You know, this is one way to deal with getting the wrong type. Throw an error. You know, another issue is to have a compiler to make sure that you cannot get the wrong type. So have types in your language to guarantee that you don't get the wrong type at runtime. Another possibility is if you do get the wrong type at runtime, immediately stop the program. And then here, this point of view, if you get a runtime type error, ignore it. Just shoehorn any value into some, you know, just somehow figure out a way to make use of whatever value you got back. You know, no matter what you got back, if it's not a Boolean, force it to be one. You know, if you're asked to multiply two things, figure out a way to do it. You know, just figure out a way to make those two things multiply. Yeah, and I suppose you could just use this. If you can't come up with anything better, use not a number. The weird thing is not a number is actually something from the floating point language. And I don't know if this is what JavaScript is doing, but in languages like C and C++, the value NaN is what you get when you do things like 1 divided by 0. Now, see, JavaScript made that infinity, but in C, you'd get not a number there, okay?
Yeah, so I had a question.
Mm-hmm.
So if you get like not a number returned in JavaScript, it's just going to keep rolling on with it. Like, but if you got a number, if you're expecting a number returned, but you get an and, then it error exceptions out.
No, it doesn't. No, in most places, not a number doesn't. Well, it depends how you compiled your code.
Like you can
check for not a number. So
yes.
in C programs, the really good way to write C programs, if you're doing a lot of numerical calculations, is if you do a calculations and you're afraid it might have returned not a number, you check for it. You can also compile your code, I think, to throw an exception if you get not a number. But not a number doesn't automatically throw an exception. It's a legitimate floating point value. So if you look up NaN, if you just Google NaN, well, that's not good. See, it's mostly from floating point arithmetic. Okay. See, systematic use of NaN was introduced by IEEE 754 floating point standard. Okay. Now, I got a feeling that JavaScript's not a number is not floating point. I have a feeling that JavaScript is using NaN in a different way. In the C language, NaN is a floating point number. It's a form of floating point number. And the same thing is true in JavaScript. NaN is a form of a floating point number. Okay. Let's see if they have any mention here of JavaScript. No. So, so this is all about this. This is the IEEE floating point NaN. Okay. And let's see. Global property is a value representing not a number, but it's probably not a floating point number. It just seems to be a global value. Yeah, whereas in C and in Java, NaN is specifically has type floating point. You know, it's one of the floating point numbers. It represents a failed floating point calculation. So it's a floating point number that represents a failed floating point calculation. Whereas in JavaScript, even though they call it seems to be just a catch-all. It just says it's a property. Well, it's a property. It's just saying it's a value. So my guess is it acts a lot like the Java not a number and the JavaScript not and the C++ not a number, but it's probably not a floating point number. Notice that they don't. Let's see. It says here there are 5 different types of operations that return not a number. That's nonsense. We got not a number from all kinds of different things. There weren't any one of these 5. So I'm not sure what they're talking about here. We got back not a number from all kinds of things that weren't any one of those. Unless they mention here, any operation that involves a string and is not addition. Okay. But I don't know if that's what we're doing here. If all this fell under somehow string and arithmetic operations, I don't know. Okay. Okay. So JavaScript is weird. You know, it seems to try as hard as possible not to throw runtime type errors, which means that it's constantly checking runtime types, and then when they aren't what it wants them to be, it just somehow manages to manipulate them to become what they want it to be. So if it isn't, if this thing doesn't give you back a Boolean, it forces it, it makes a choice somehow. It either replaces it with true or replaces it with false in some bizarre way and just turns it into a Boolean value, but it doesn't throw an error. Okay. So again, you could either have you could have types in your language so that static analyzer can guarantee there's no type errors, or you can have your language do runtime type checks and throw an error when they don't have the right type, or you could do like JavaScript. You do a runtime type check, and then if it's not the type you really want it to be, you find a way to manipulate it into a type that you want it to be. So you just do strange they're generally called conversions or casts. You just take the value you got and cast it to what you want. Yeah. So then you have to have a bunch of rules that say if you got back a string, how do you cast a string to a bool? If you got back an integer, how do you cast an integer to a bool? If you got back an object, how do you cast an object to a bool? So if you don't get back the type you want, instead of throwing an error, you do some kind of runtime cast. That's the JavaScript point of view. Okay, so that's what the homework assignments hopefully gets you start thinking about, is that you're writing one kind of thing. The original interpreter did one thing. The original interpreter did nothing but tons of runtime checks. Now you're doing the static analyzer that catches a lot of them at analysis time. We're still left with the types. After you write your static analyzer, there's still the type errors. That's the next big thing if the course lasted longer, that would be the next big thing, is like, okay, let's put the types in the language and let's see if we can type check ourselves, which is quite a bit of work. It's a non-trivial thing, but it's interesting. It's the next step, and it would be worth it if we had more time in the semester. Okay, well, we'll quit there. So that was. I mean, I hope that helped you get a sense of what it is what the goal of this is. It really is all these different languages, understand them, have a way of like, what's TypeScript have in common with Python? What's TypeScript have in common with Java? What are the choices? What are the designs? What are these languages trying to do? Okay. Well, yeah. What?
Are we in strict mode for the due date for this last assignment?
No, it's due today, actually, right?
Yeah, yes.
So, yeah, no, it needs to be in, actually, not for another week or so. Yeah.
Okay, that's good to know.
Yeah, let's see. This is the last week of the semester. This is final exam week. I probably need everything by, say, Wednesday of next week, because I have to have grades in by the following Tuesday. So I need everything. I would need things turned in by the 5th. After that, I may not be able to have time. After that, I'm going to be in the mode where I'm just going to be grading grading what's been turned in. Okay, so I can accept things up to about then.
Thank you.
That gives me 5 days to grade it, because I turn in grades on this day here, Tuesday, May. I turn in grades there. No, wait a minute. No, I turn in grades there. We're here. So like this day's the last day I could probably accept homework. And then that gives me a few days to do the grading. I turn in grades that Tuesday morning. Okay. So yeah, when I made that due date, I was wondering if I might have one small programming assignment left at the end for the last week or two, but I don't have time. I wouldn't have time to grade it anyway. So I'm not going to make another small programming assignment because I wouldn't have time to grade it. Okay. So this one will be due. Yeah, the real due date's going to be the 5th. Okay. Any other questions before we quit? Okay. All right. So I'll try to show you some more. Well, if there's any more questions about the analyzer on Wednesday, if there's any more questions about it, we could still look at the analyzer some more too. And then also, I was going to show you something to do with higher order functions. There's something to show you that why we're interested in higher order functions. Another example of why we would be interested in higher order functions. Okay, so I'll stop here. Okay, see you on Wednesday. Bye.